It wasn't.
We have the brain. He's just.
Restarting this.
Okay. Welcome back, everybody. My name is Michele Battistini. I'll be sharing this second part of the session today. The first presentation is called Aristotle Accelerating CFD Simulations of Reactive Flows through Cell Agglomeration and Adaptive Chemistry Techniques. And the presenter is Alberto Pozzo from Technical Milan.
Thank you very much for the introduction. Good morning, everybody. Can you hear me?
Yes.
Okay. Okay. So good morning. My talk is about, as suggested by the title, is about numerical techniques for accelerating CFD simulations of reacting flows. So I know this meeting is mainly about propulsion systems and internal combustion engines, but the techniques I'm going to talk about are more general. They, in principle, can be applied to any type of reactive flow with detailed chemistry. I mean, every time you want to use direct integration of detailed kinetic mechanisms with hundreds of species, thousands of reactions. So even if I will not present examples or applications about propulsion systems, my hope is that at the end of this presentation, you can have ideas for, let's say, accelerating or speeding up your OpenFOAM-based codes for internal combustion engines. We all know that today there is an increasing interest in including detailed chemistry in CFD simulations. And this is especially true for combustion and internal combustion engines or propulsion systems. So more specifically, detailed chemistry is important to account for the interactions among the different components of real fuel or for modeling in a proper way biofuel chemistry, which is complex because of oxygenated species or unconventional species if compared to traditional fossil fuels. Chemistry is important for modeling pollutant emission formation and emissions, or more in general for capturing complex phenomena, instabilities, and so on. But we know that integration of detailed chemistry in reacting in CFD simulations of reacting flows is expensive from the computational point of view, and we need special numerical techniques. One of the options, which is quite common in the OpenFOAM framework, is the operator splitting approach, according to which we split basically the time step. We split, the operation at each time step in a transport and chemical step. And most of the computational time is spent for integrating the chemical step. And the cost increases with the number of species that you have in your kinetic mechanism. So if we really want to accelerate our CFD simulations with detailed chemistry, we first of all, we have to try to accelerate the chemical step. And so this is the topic of this presentation. We have different options in principle. We can work directly on the acceleration of the OD solver that we use for integrating and solving the chemical equations by using specific techniques, by trying to exploit as much as possible the sparsity pattern of kinetic mechanisms, replacing maybe the integrator with artificial neural networks or other tools, similar tools. But we have also other options. We can try to reduce the number of cells, which means that basically, thanks to cell agglomeration techniques, we can combine, we can group together cells which are similar from the thermochemical state. And so we combine them and we cluster, we create clusters, and so we integrate at the level of clusters instead of single cells, and so we can save time, or we can locally reduce the complexity level of chemistry, which means basically we locally reduce the size or the complexity of the kinetic scheme by removing unimportant reactions or unimportant species. Now, in this talk, I would like to introduce this technique here, which is called PCA squared, and which is based on the idea to combine principal component analysis and cell agglomeration. Then I will introduce this additional technique which tries to combine the advantages of both cell agglomeration and dynamic adaptive chemistry. Okay, so first option, as I mentioned, the idea is to first of all to try to use principal component analysis to speed up the conventional dynamic cell agglomeration technique. Just to recap what I'm talking about, dynamic cell agglomeration means that we, instead of solving the ODE system of equations in each cell, we group together cells having similar temperature composition in clusters, and then we perform the numerical integration for each cluster instead of each cell, and then we remap back to the original cells the solution. Of course, this operation is not always trivial. You have to account for special techniques in order to account for the initial stratification in composition and temperature that you had here. But I mean, there are different options. This is not anyway the core of what I would like to discuss. The point is that dynamic cell agglomeration requires the identification of a criterion to, let's say, to select cells which are similar, okay, that we can group together in a single cluster. And typically you look at composition and temperature, but if you are using a very detailed kinetic mechanism, this is very expensive. If you look at mass fractions of all the species and temperature, basically you have a computational overhead, and so you are losing the advantages of this procedure. So you select typically a limited number of key species, significant species, and you apply the agglomeration, the agglomeration on those on this small number of species. But this is arbitrary. Not always it is easy to identify the optimal subset of species. Not always the same species are relevant at every time in your simulation or in every area of your computational domain. So the idea was to use principal component analysis to make this kind of approach more rational or less arbitrary. And so the idea is super simple. At each time step, we build a big matrix which is just which includes the temperature and composition for every species. Then we apply principal component analysis. Of course, we do all the typical operations like normalization or shifting of variables, but we apply at the end principal component analysis. We identify the principal components, the first principal components, and those first principal components becomes the features, the variables on which we apply the dynamic cell agglomeration. The advantage of this procedure is that we just need to prescribe a single parameter, which is the variance, the level of variance we want to keep in the PCA operation. Okay, so 80%, 90%, 100%, of course, this is too much. Okay, so we just prescribe the level of accuracy at the end we want to keep, and we perform principal component analysis. So according to the level of variance we want to keep, we will have a given number of principal components, 2, 3, 10, it depends, which are able to satisfy this our request. And so these 2, 3, principal components becomes the variables on which we apply the agglomeration. So this is a first parameter, and then we need a second parameter, which is the typical tolerance that we use for performing classical dynamic cell agglomeration. Okay, so the advantage of this technique is that at the end we can control everything, a compromise between accuracy and computational efficiency, just using two parameters. So let me show an example to better clarify this point. So this is a laminar coflow flame, dynamic coflow flame, in which we imposed fluctuations in the inlet stream velocity. And so we used a detailed kinetic mechanism, 200 species, 6,000 reactions. And we applied this kind of technique, this PCA square technique. So here we have just a comparison on a qualitative basis between the fully resolved simulation on the left and the PCA squared simulation on the right for temperature and several species at different time levels. And so on a qualitative basis, the agreement seems quite good. But we can also do something more quantitative on a quantitative basis. So here we defined in some way a measure of the global error between the fully resolved and PCA squared solutions. And in particular, here in the first plot, we reported this global error as a function of the level of variance that we prescribed by fixing the tolerance for the cell agglomeration phase. And you can see that the error, the global error, decreases with increasing variance. And this is what we expected. And it decreases in a regular way, quite regular way. And the same is true also if we do the opposite. If we fix the level of variance we want to keep and we decrease the tolerance in the cell agglomeration phase. Again, the error decreases for decreasing tolerance. And this is what we expected. This is what we like. So this is basically what I mentioned before. Using just two parameters, okay, we can control, okay, the quality of our reduced simulation. And so this reduces the level of arbitrary choices that we have to consider in applying this technique. In terms of computational performances, of course, since we are working just on the chemical step, the transport step is not affected by this technique. It's always the same independently of the parameters that we use in PCA squared. There is an additional cost that we have to consider, which is the cost for performing the PCA, which is not negligible in general, but not comparable to the chemical cost, especially if we increase the number of species in the in our kinetic model. Then we have a cost for the clustering operation, but this is very, very small, negligible. And then we have, of course, the cost for chemistry, for the integration of chemical step, which depends, which is a strict function of the tolerance levels that we choose. Speed up, of course, since we are accelerating just the chemical step, we have a maximum, a theoretical maximum speed up that we can reach. And so in this case, for example, is around 20, but of course we never reach this limit. The speed up we can reach, of course, depends on the level of tolerances that we choose. And here you can see that if you use, in this specific example, of course, if you use strict tolerances for the cell agglomeration phase, actually the speed up is not, let's say, so small, factor around 5, 6, which is not bad. But as I mentioned before, we can also do something more. I mean, we can try to combine the advantages of this cell agglomeration technique with dynamic adaptive chemistry. So dynamic adaptive chemistry, everybody knows that in dynamic adaptive chemistry, we simply look at the at the temperature and composition in every cell. Okay, and we try to reduce on the fly the kinetic mechanism, and so we remove reactions and species which are not important. Very nice idea, but there is a cost, a computational cost that you have to pay for performing this kind of operation on the fly. And this cost can be significant if your kinetic mechanism is complex, if it includes thousands of species. Okay, so the idea here is to reduce this additional cost or remove this additional cost by building in a pre-processing phase a library of reduced kinetic mechanisms. And then during the CFD simulation, we just pick from the library the most appropriate reduced kinetic mechanism for every cell. And this is what we call Spark. So more specifically, this Spark technique is based on two different phases. We have a pre-processing phase. And in this pre-processing phase, first of all, we generate a training data set. I mean, we generate a data set using simplified systems, which are computationally not very expensive. Typical systems are counterflow diffusion flames, flamelets, remixed laminar flame, flat flames, and so it depends on, of course, on your application. Then there is the next step, which is in general, in this step, we try to classify, to cluster, let's say to classify the different points that we created according to a similarity criterion from the chemical point of view. Okay, so in the example I'm going to show, we basically do a very simple type of classification, which is simply a remapping. I mean, we remap the training data set according to two new variables, which are, for example, the mixture fraction and the progress variable, but different options are possible. Then we partition this training data set, which was reorganized in some way. And so we identify, similarly to what I presented before, we identify clusters of observations which are similar from the kinetic point of view, and we produce for each cluster a reduced kinetic mechanism. And so we have, at the end of this operation, a library of reduced kinetic mechanisms. Then we have the CFD phase, second phase, and in the CFD phase, we apply the cell agglomeration, similarly to what I presented before, and then after we have identified the clusters, we select from the library of reduced kinetic mechanism the most appropriate reduced kinetic mechanism. We perform the usual operations, numerical integration and back mapping. Again, the point here is that we can control everything with two parameters only. In the pre-processing phase, we simply choose a tolerance level for reducing the kinetic mechanism. Typically, we use the DRG technique or DRG-EP technique. So we prescribe a tolerance for governing the level of accuracy we want to keep in the reduction process. And then we have a second parameter in the CFD simulation phase, which is the cell agglomeration tolerance, similarly to what I presented before. So, of course, the key point in this kind of technique is to generate a proper training data set. Okay, so this is a very important step. In the examples now I'm going to show, which are non-premixed frames, we generated the training data set using laminar flamelets at different scalar dissipation rates, including both steady state flamelets and unsteady flamelets in order to cover in a more appropriate way the composition space. And we remapped everything according to two variables, which are two primitive variables, if you like, which are mixture fraction and a progress variable. But of course, this is just a possible option. You can use also different approaches. We tried also different approaches. It depends on the system you want to simulate. And then once we reorganize the observations in the training dataset, we can produce the reduced kinetic mechanisms. And so here in this plot, for example, every point corresponds to a different reduced kinetic mechanism, and the color is the number of species in this reduced mechanism. So the original one had more than 200 species, and here you can see that in some regions here of this space, the reduction can be significant. Okay, so an example. First example is temporarily evolving non-premixed planar jet flame, which was proposed by Hawkes several years ago. This is a quite well-known benchmark test for people doing DNS of turbulent flows. So we studied this case here. What we did was basically a quasi-DNS. This cannot be considered a real DNS because I mean, the discretization schemes for space and time in OpenFOAM are not really appropriate for a real turbulent DNS, but this is not the point here. The objective of the analysis is to compare the fully resolved simulation with this reduced simulation, so we don't care about this. We used a detailed kinetic mechanism, not so large, 60 species, 400 reactions, more or less. And here, just to give you an idea, we try to compare the fully resolved simulation with reduced simulations. Here, actually, those are results which refer to temperature, which is partially averaged along proper planes. Let me say simply that this is just a simple way to try to compare the results for this three-dimensional unsteady case. So fully resolved simulation and reduced simulations with different values of the parameters. Again, from the qualitative point of view, there are no big differences. I mean, some details here show some differences here, but the overall agreement seems quite good. Again, we can do some comparison on a more quantitative basis. So we introduced a relative error, a global relative error. And here, this global relative error is reported as a function of the tolerance for the reduction, for the chemical reduction phase here. By fixing the tolerance for the cell agglomeration phase. And again, you can see the trend is quite regular. I mean, we have a decrease. Again, also in this case, the overall speed up that you can read here is not so bad. Even if you use strict tolerances, you can get a factor of 3, 4. Again, which is not bad if you consider that the kinetics was not very detailed. A more interesting and challenging example from the chemical point of view is what I reported here. This is, again, also a very well-known simulation in the literature. Basically, we have a 2D turbulent non-premixed flame in decaying isotropic turbulence. So we start with a strip of normal heptane surrounded by air. Okay, and so we have the evolution of this system. Here in this example, we were interested in testing the ability of this technique to capture the formation and evolution of soot. And so for this purpose, we used a detailed kinetic mechanism, including a discrete sectional model for describing formation of soot particles and aggregates. And so thanks to this approach, in our simulation, we are basically able to model to, let's say, estimate the particle size distribution of soot particles and aggregates in every point at every time in the computational domain. This is just an example, of course. Here you can see the particle size distribution in function of soot at 3 different times. And here on the horizontal axis, we have the diameter of particles or aggregates, and here on the vertical side, the number of particles. Of course, as you can see here, as expected, the mean diameter of the soot particles and aggregates increases with time because of surface growth, agglomeration, aggregation. But the point is that actually this technique, this reduction technique, SparkCA, is able to describe in a proper way with good agreement, not only the main fields, as we saw before, temperature or main species, but also fields related to soot, like in this example here, soot particle number density, fully resolved simulation, and reduced simulations with different parameters, and even the particle size distribution function of soot. And so that was the purpose of our analysis. Last point, and then I will close. We can also see in this plot here the blue line, which is the number of clusters that we have in time during the evolution of this system. So as you can see here, we start from a very small number of clusters at the beginning of our simulation, because at the beginning everything is stratified, and so you just need a small number of clusters, and so the speed up that you have is quite high, which is the orange line. But during the evolution of the system, the complexity in the composition space increases, and so we have a larger number of clusters and decrease in the speed up that we get. Okay, so to summarize, I try to introduce a couple of examples of acceleration techniques on which we are working. So the examples do not refer, of course, to propulsion systems, but in principle, those techniques could be extended to internal combustion engines, propulsion systems. There are additional complications, of course, but in principle, this extension, in my opinion, is possible. So before closing, I would like to acknowledge my colleagues at Crack Modeling Lab here in Politecnico di Milano, and I would like also to acknowledge Heinz Pitsch, Alessandro Parente, Giuseppe D'Alessio, and Temistocles Gringa, who contributed to this work. Last slide. Maybe you already know, but in July this year, in Milano, we'll have the International Symposium on Combustion. So I hope to see you again in a few months. So thank you very much.
Thank you. Are there any questions? We have time for a couple of questions. Yes.
Yes, thanks for the talk, really interesting. I'm really curious about the clustering of the two methodologies. If I understood, now at the moment it's not possible to couple together because the clustering will be different if I use the Spark and if I use the reduction of the chemistry, right?
Okay, so you are saying that you are asking if we can combine PCA squared with
yes.
the second. Okay, what I presented, you're right. Actually, what I presented in the second part is cell agglomeration operation carried out directly on species, or in this specific case on mixture fraction and progress variable. But in principle, during in the training phase, in the pre-processing phase, if you reorganize your data using principal components instead of mixture fraction or progress variable, actually you can use principal components.
Even so it's possible to remap using the principal components, so the clustering will be compatible with each other. In
these examples, I mean, the remapping using mixture fraction and progress variable was very effective. So maybe there was no need to use more advanced techniques. But in other cases, maybe just using these two primitive variables is not enough. And so you may consider more complex approaches. The advantage of PCA squared with respect to the second technique is that you don't need any pre-processing phase. You can do just everything on the fly, which is very convenient. Yeah,
thanks.
Right.
Yes.
Yeah, nice work. I was just, when you do all this adaptive reduction, the number of species you keep are all different.
Yeah.
So when you switch over from one regime to another within the same cell, you need to retrieve what was missing. This is a classical like steady state approximation. So is that already built? I know DRG does that. There is a retrieval of these steady state species through non-iterative procedure. Otherwise, if you have to solve all these nonlinear algebraic equation, it's an overkill. So I wonder if you actually have a way to address those issues.
No, maybe I think if you need, let's say, if you want to simulate a system in which you expect